Hey everyone, it's Mr. Canfield. So, sorry for that long intro. All right, today we're gonna be looking at something called L'Hopital's rule. But before we do that, it does start with a couple of questions. So I just want to look at these really quick. So the first one says, find y prime given y is equal to the natural log of x squared minus 4x plus 1. So if we do that, remember that the derivative of ln, the derivative of natural log is just 1 over the inside stuff. So I can just do literally just 1 over x squared minus 4x plus 1, and that would be y prime if the chain rule didn't exist. But the chain rule does exist, so then I got to do multiplied by the derivative of the inside, which is 2x minus 4. So I would not write it like that. I don't normally write it like that. What I like to do is I like to say y prime is equal to, and then I'll write out the x squared minus 4x plus 1, and on the top I'll write the 2x minus 4. This is the traditional way you're going to see this. Almost no one is going to write it like that as an answer on a multiple choice question or anything like that. So just get used to that. So I just wanted to review a couple of older ideas that we need moving forward. So our next one says y is equal to e to the x squared minus 4. So same inside stuff, just a different function. And so similarly, if we remember our derivative of e, it's just itself. E to the x, when we take the derivative, is just e to the x. So e to the x squared minus 4x plus 1, when we take the derivative, is just e to the x squared minus 4x plus 1. Wow, it's the same. Okay. The only difference is now there's chain rule, so I got to multiply by the derivative of the inside. And again, I wouldn't write it like this. In general, what I'll do is I'll write the original, and then I'll put the derivative out front. Again, this is the way that you're going to see it most of the time. So it makes it a little bit easier to read, makes it a little bit more easy not to mix up your exponent with other stuff. Okay. Then some kind of twistier ones that I want to talk about. I kept the question the same, but this time we're given y double prime. So if I want to find y single prime, that means I'm going to have to integrate both sides. This side with respect to y, this side with respect to x. So this side becomes y prime. Wow, that was hard. Okay, then this side. All right, maybe I need to just remind you that if y is equal to, let's say 3 to the x, then y prime is also equal to 3 to the x, except then an ln 3 pops out. So in order to go backwards, if we had said y prime is equal to 3 to the x, then to get y, to get regular y, to get from y prime back to regular y, it is still, whoa, let's try this again. I'm just kidding. Okay. To go from y prime is equal to 3 to the x, to get back to a regular y, it's still going to be 3 to the x. But let's think about this. When I take this derivative, an ln 3 pops out. So in order to go backwards, I'll need to divide it by the ln 3. That way, when I take the derivative of this, we get, we can think about that. I take the derivative of this. ln 3 is just a number. So it's going to be 3 to the x over ln 3, that happens. It just stays the same. And then we multiply it by an ln 3, and the ln 3's cancel. So the only way to antiderive a 3 to the x is to keep it the same and drop an ln 3 underneath. So that is almost this situation. However, it's not 2 to the x, it's 2 to the 4x. So we're going to have to deal with a u substitution to figure this out. So we'd say u is equal to 4x, so then du is equal to 4dx. And we could solve this for dx and get 1/4 du is equal to dx. So then I could say, okay, well, then this is going to be equal to the integral of 2 to the u. Instead of writing dx, I'll write 1/4 du. I'll put the 4th out front, put the du here. Good to go. So then the antiderivative of 2 to the u is just going to be 2 to the... Let's see if I can make this into a 2. Yeah, there we go. I didn't make a mistake. I did it on purpose. All right, 2 to the u divided by ln 2 with our 1/4 out front. There. And then we'll need our plus c, of course. So that's going to be 2 to the 4x, because that's what our u was, over 4 ln 2 plus c. All right. Cool. And then our last one, it looks really bad, but let's see what happens. Let's say u is equal to x squared. Well, that means that du is equal to 2x dx. So if we were to integrate this guy, we're going to get y prime is equal to, sorry, dy over here, dx over there. There, now it's real. Okay, no open-faced sandwiches. So now if we do that, we get the integral. We're going to get 2 to the u, and then our 2x dx cancels completely du. Oh, so that's just going to be 2 to the u over ln 2 plus c, which, if we're careful, that's 2 to the x squared, all of that over ln 2 plus c. This one's actually easier than the previous one because it cancels perfectly. So now with that little review out of the way, let's jump into L'Hopital. All right. Introducing, from Wikipedia, Guillaume L'Hopital. So Guillaume, which doesn't really matter, it's French William, L'Hopital, or as we're going to say very often, L'Hopital, or the hospital, because it like basically looks like hospital. So anyway, he figured this rule out. Let me see, I want to read here. Oh yeah, the real name for this is indeterminate forms. So indeterminate, remember, we talked about this at the beginning of the year. Indeterminate means I can't determine it. It means that we are not sure. It doesn't mean no, and it doesn't mean yes. It means I don't know. That's what it means if we can't determine something. We're not sure. So we're going to discuss a special technique for tackling indeterminate limits. Basically all the limits we've done, barring a couple of them. So we'll review with a couple of limits. I really wanted to include this picture because like that hair, wow. I learned recently that a lot of the times people like this wore wigs because the shape of their skull was pretty bad because of different diseases they had and stuff like that, and the wig covered it up. I don't know if that's true, but I heard it, which makes me think maybe he's got a couple of like scars under his head. Anyway, all right, so we're going to find some basic limits. Find the limits. Okay. Our first order of business whenever we find a limit is we check direct substitution. All right, so let's see. Can I plug in 0? 0 squared minus 9 is minus 9. Then 0 plus 3 is 3. Oh, hey, it's a number. It's -3. Done. Okay. No work required. Find the limit as x approaches 1. Well, let's see. 1 squared minus 9. Oh, I can do that. 1 plus 3. So 1 squared minus 9 is -8 over 3. Oop, no, that's 4. It's -2. Okay. Very possible. Can I plug in 3? Let's see, 3 squared minus 9 is 0, so I got 0 over 6, which is a number, it's 0, it's fine. Okay, cool, the limit as x approaches 3 is 0. And then the limit as x approaches -3, we get here, we go, let's see, -3, we get 0 over 0. Ah, no, it breaks. This is called an indeterminate form of 0 over 0. It doesn't mean that the limit doesn't exist. It means that f of -3 doesn't exist. I can't plug in -3 and get a number. But with a little clever working, x plus 3 times x minus 3. If I factor the numerator, because it's a difference of squares, and we cancel out that, now I have the limit as x goes to -3 of x minus 3. Well, gee, -3 minus 3 is -6. The limit exists, and it's that. So remember that just because the function doesn't exist somewhere doesn't mean that the limit can't. Now we have a continuity issue here. We'd say it's discontinuous, so I couldn't use different things like the intermediate value theorem, but oh yeah, and the function won't have a derivative when x is equal to -3, but we can still go through and find the limit. So the first thing we do when we're doing limits, we check direct substitution and then use algebra to fix it, to make it work. All right, this encompassed like September. So today I'm gonna spoil it just a little bit, and I'm gonna show you something kind of weird. L'Hopital, I don't remember how he figured this out. I don't know if I ever learned it. I don't think I know how he figured it out, but L'Hopital said, hey, let's take the derivative of the top and derivative of the bottom. We got 0 over 0. We don't know what that is, but what if we took their derivatives? So don't do quotient rule. Just take the derivative of the top. Derivative of the top would just be 2x. Derivative of the bottom would just be x. No, it wouldn't. What's the derivative of x plus 3, Canfield? It'd be 1. Okay. And what is the limit as x approaches negative 3 of this mess? Well, plug it in. We may have just learned an alternative route to getting limits. And it's amazing. All right, so L'Hopital's rule. Let's say what it is and then do it a whole bunch. All right. L'Hopital's rule. You can only do L'Hopital's rule if it's 0 over 0 or infinity over infinity or any other matching of infinity over infinity. If it's 0 to the 0, believe it or not, that's an indeterminate form, but it's not one of these, so L'Hopital's rule doesn't apply. Infinity minus infinity is also an issue, because are these infinities the same size, or is one bigger than the other? We're going to have to kind of investigate. This might wind up being 0, it might wind up being infinity, it might wind up being negative infinity. There's lots of options, and we have to investigate. This one, 1 to the infinity. This is actually an indeterminate limit, which does not feel right, because 1 times itself infinity times should just be 1. But because of some things that we'll see later, this requires further investigation. And then 0 times infinity is another situation where, on its own, you can't determine it. Which wins, the infinity or the 0? Because remember, we're talking about limits. We're talking about as we go to something, not what is it actually when you plug the number in. Let's just look at 0 over infinity really quick. I mean 0 times infinity. 0 times infinity. It's fair to say, you know, if we're just kind of having a conversation about this, I could say this is 0 times 1 over 0. Because 1 over 0 is essentially infinity. And so this is now 0 over 0. And now I'm able to use L'Hopital's rule. Or I could manipulate it this way. 1 over infinity is 0 times infinity. Now we have infinity over infinity, and we can use L'Hopital's rule. So we're going to be encountering things like that every now and then. Those of you moving on to Calc 2, we spend the first few weeks just doing L'Hopital's rule and learning lots of really specific instances of it. Really interesting stuff, and it comes up all over the place. It's actually a really useful rule in different Calc 2 stuff. So the big deal with L'Hopital's rule, now that we know when we can use it, is that if you have two different differentiable functions, and as the limit goes to some value, or as x goes to some value, their limit approaches 0 over 0 or infinity over infinity, as long as it's one of those, we can take the derivative of the top, the derivative of the bottom, and it's going to have the same limit as the original had. That's very different from saying it's the same function, it has the same y value, none of that. We're just able to find a limit using this. So L'Hopital's rule is very, very specific in what it tells us, but it's really, really good at it. So here's our first example. All right. So you may remember this from early on in the school year, the limit as x goes to 0 of sine of x over x. We did talk about this, but let's say you don't remember. Well, let's try direct substitution. Can I plug it in? Sine of 0 over 0. Sorry, I'm so used to writing thetas because I'm teaching pre-calc 2. Sine of 0 over 0. Let's see, sine of 0 is 0, so we get 0 over 0. Lots of zeros. Oh, hey, that's indeterminate. That means that we can do L'Hopital's rule. So, L'Hopital that, John. Whee! All right, that's the official symbol for L'Hopital's rule. Just kidding. Also, in case you're missing it, I drew that because it's called L'Hopital. It's hospital. Okay, I probably already said that. All right, so if we take the derivative of the top, we get cosine of x. Take the derivative of the bottom, we get 1. And if I plug in 0 now, cosine of 0 is 1. And if you remember from earlier in the year, this is true. The limit of sine of x over x as x approaches 0 is 1. So let's look at our next one. Limit as x approaches 2. So I'm going to try direct substitution first. I'll get 5 over 0. Well, L'Hopital's rule says that it has to approach 0 over 0. This doesn't do that. So I guess I can't do L'Hopital's rule on this one. And sure enough, if you were to graph this to look at it, let's see. So if we were to graph this and look at it, as x approaches 2 right here, we get a limit that doesn't exist. And so L'Hopital's rule can't tell us anything about this one, but our knowledge of asymptotes can. And so since this is doing this sort of thing, we can say the limit does not exist. The left and right hand limits do not agree. The frowny face is not important, though. All right, our next one. Oh, I'm putting myself to sleep. I'm so boring. All right, limit as x goes to 0, e to the 2x minus 1 over x. All right, let's try direct substitution. Again, we always need to check that because sometimes this happens. If we had done L'Hopital's rule here, we would have gotten 1, and it's just not true. So, all right, if I plug in 0, I get e to the 2 times 0 minus 1 over 0. Well, e to the 2 times 0, that's e to the 0. Right, e to the 0 minus 1 over 0, and e to the 0 is just 1. 1 minus 1 over, oh, it's oo over oo. That means I can L'Hopital it. So the bottom's easy, right? So we'll say, now, I sometimes forget to write the limit thing when I'm doing these informally. I really need to make sure I'm including the limit thing because otherwise I'm saying this is the same as when the limit isn't there, and it's just not true. So if I take the derivative of the top, we'll just e to the 2x and then times the derivative of the insides, which is 2. So I get 2 e to the 2x, and now I can substitute in 0 and get 2 e to the 0, or just 2. And so the limit of this function is, in fact, 2 as x goes to 0. All right, let's look at our next one. If we plug in 2, we get the natural log of 2 minus 1 over 2 minus 2, which is the natural log of 1 over 0. Well, natural log, remember, that is e to some power. That was my chair, I promise. That was e to some power gets me 1. The power that we take e to get 1 is the 0th power, so we get 0 over 0. So we are allowed to L'Hopital this. And this is where I really love that we don't have to do like quotient rule or anything. Because if we do L'Hopital on this, well, the derivative of the top one is just, well, the x minus 1 goes on the bottom, and then the derivative of the x minus 1 goes on top, which is just 1. And then derivative of the bottom is just 1. And you can clean this up if you want to. Or you can just plug in 2. 1 over 2 minus 1 all over 1. That's my bigger fraction bar. Sometimes I feel like I'm drawing like a dojo or something. So that's 1 over 1 over 1. 1 over 1 all over 1, which is just 1. Yay! Now here, I don't know if you can see it, but there's a face that starts to emerge. Sorry, okay, so we got 1 there. Let's keep going. Let's try a couple where we plug in infinita. All right. Yeah, these are important for us to think about. Let's see. If I plug it in, just kind of doing direct substitution, which, like, we're not actually allowed to do that. These are not numbers, but they help us think about it. The natural log of infinity. Okay. Well, e to what power gets us infinity? Turns out e needs to go to the infinitieth power to turn into infinity. So it's infinity over infinity. But if we think about this, e to a power getting us infinity, that's different than just infinity itself. It's a different kind of infinity, and maybe that's going to mess with the way this works. Maybe this is actually going to approach some number. If we think about these growing, they don't grow at the same rate. X winds up growing a lot faster than the natural log of x, because the power that e needs to go to get to the less number grows pretty slowly. So let's see what happens if we L'Hopital that, since we got infinity over infinity. We're going to get 1 over x on the top, the limit as x goes to sideways 8. And the bottom we're going to get 1. And so we can rewrite that and say the limit as x approaches infinity of, I can just put that x on the bottom and get 1 over x like that. Well, what's the limit as 1 over, as x approaches infinity? We get 1 over infinity. That is a limit of 0. And so because of that, this limit here is in fact 0. Now when I look at this one, I think about which one of these is stronger, which one of those grows faster. And e to the x is definitely going to be growing faster, because if I think about this, e to the 1 versus 1, that's already at 2 point something. E to the 2 means e times e. That's just 2. So I'm thinking this is going to fly off to infinity, but let's just double check. So I'll do my direct substitution, e to the infinity over infinity. E to the infinity is obviously infinity. Maybe it's not obvious. It's 2 point something times itself an infinite number of times. It's infinitely big. We get infinity over infinity, which we call indeterminate because we don't know. So then we get, well, we can do L'Hopital then, since it's infinity over infinity. Take the derivatives. We get e to the x on top, nice easy derivative. And then derivative of the bottom is just 1. The limit as x approaches infinity. Seriously, I'm going to try to write it every time because we should be writing it until we take the limit. I almost wish I could get a stamp, just to stamp it on each step after I'm done. So now if I plug in infinity, I do get e to the infinity, and I still get infinity. And so this limit likely diverges. So this does not exist. Sorry, I used the wrong word. It does not exist. We don't use the word divergent in Calc 1. We save that for Calc 2. All right. Sometimes this happens. I love it when I give myself hints like I'm going to remember it. So let's see. Infinity squared over e to the negative infinity. That is, let's see. That's infinity squared times e to the negative infinity. Wait, I could rearrange that, right? I could write that as x squared e to the infinity. Or sorry, infinity squared times e to the infinity. Guys, infinity times infinity is infinity. It's really big, okay? If we go back to our things that were actually indeterminate earlier. By the way, I'm totally afraid that I'm wrong right now. Yeah, okay, no. Like infinity minus infinity maybe, or 0 to the 0, that's a weird one. 1 to the infinity, that's a weird one, but really, really big times really, really big, they're all positive, huge. Another way to think about this says infinity squared. If we think about e to the negative infinity, that's 1 over e to the infinity. That's infinity squared over 0. And it's just flying off to huge numbers. So let's see. All right, L'Hopital's hiding somewhere. In my Smart Notes presentation of this, you can kind of see it on the handout. There's a little outline right here. I have a little panel that I dragged down, and L'Hopital's hiding behind it. And he can be like, hello, I'm L'Hopital. All right. So if I try plugging in infinity, I wind up getting 0 times infinity. Or no, I get infinity times infinity, my bad, because the negatives cancel out. Here, I'll show you. E to the negative infinity times, times the square root of negative infinity. Can I even do that? This has to be a typo. That's just regular infinity. Yeah, we don't deal with imaginary numbers. Okay, so we'll say going off to positive infinity. Now if we look at that, we're going to get e to the negative infinity square root infinity, rewritten as square root of infinity over e to the infinity, rewritten as infinity over infinity. So at the outset right here, it's kind of hard to see, but L'Hopital is actually hiding here. We can say this is a square root of x over e to the x. It's the same thing. He was not hiding very hard in a very difficult spot in this one. So now if I take that derivative, then I get limit as x goes to infinity, and I get 1 over 2 root x. So remember, square root of x is just x to the 1/2. So I bring the 1/2 out front, and then subtract 1 from that and get negative 1/2. So then I can say that this is 1 over 2 x to the 1/2. And that's where I get that from. Then our denominator, when we take the derivative, we still have e to the x. So this is going to be, if I combine these fractions, this is 1 over 2 root x divided by e to the x, right? That's all that's saying, which I could rewrite that as 1 over 2 root x times the reciprocal. And then if I combine those, I get 1 over 2 e to the x root x. So now I have 1 over 2 e to the infinity. I need my stamp. Limit as x goes to the infinity. Limit as x goes to the infinity. Limit as x goes to the infinity. Limit as... Oh wait, now I'm actually plugging it in. I don't need the limit anymore. Now that I'm plugging it in, I get to remove the limit. E to the infinity, square root infinity. G, 1 over 2 times infinity times infinity. I wonder what that is. It's 1 over infinity, which is 0. So, you're going to get to a point where you can do these a lot faster. I'm just trying to show kind of all the little details. And then we just got some practice. So, remember, we always want to do direct substitution first, and then we got to be really careful about our numerators and denominators. Yeah. Have a great day. Bye.